Hello everyone, my name is Amir Mir. This video I'm going to present Type4Py, our technical paper for ICSE'22. As we know, Python is easy to use and it allows rapid prototyping. Due to the lack of static types, Python developers often encounter type errors. Also, lack of static types causes runtime exceptions and weak IDE support. Python supports optional type annotations, meaning that developers can add types to their code base gradually. However, this is a daunting task, and motivated by this, researchers have recently proposed ML-based type inference models to predict type annotations. Also, there are some static type inference tools for this task. At the time of publishing this paper, there are two state-of-the-art ML-based type inference approaches, namely Typeless and Typewriter. Typeless is based on graph neural networks, and Typewriter uses hierarchical neural networks to predict type annotations for Python. In this space, we have identified two problems and challenges. Giving the correct type in the top one is very challenging for ML models, and ML models usually give a list of predictions like top 10. However, the first suggested type may not necessarily be correct. On the other hand, developers tend to use the first suggestion by tool. Moreover, type annotations provided by developers are not always correct, and this may introduce threat to the evaluation of ML model. In this paper, we propose Type4Py. It is based on deep similarity learning and hierarchical neural networks. It simply learns to discriminate between similar and dissimilar types in a high-dimensional space, namely type clusters. We also provide a type check dataset both for evaluation and training. And we also provide a visual statistical extension that provides ML-based type completion for Python developers. There are quite a number of research works on ML-based type inference for JavaScript and Python. As mentioned before, Typewriter and Typeless are state-of-the-art approaches for Python. And notably, Type4Py supports unlimited type vocabulary, meaning that it has no limitation in terms of number of types that the model can learn from the training set. Now I'd like to talk about our proposed approach Type4Py and what features it uses to predict type annotations. This is the overview of our proposed approach. First, by analyzing the abstract syntax series of Python source files, we extract type hints like identifiers, code context, and visible type hints. Next, we generate token embeddings or vector representation of type hints, and we feed them to the Type4Py model. Finally, the Type4Py model maps the type of variables, parameters, and return values into a high-dimensional space, namely type clusters. We have provided one code snippet here to better explain type hints or features. Visible type hints are extracted by analyzing input statements from a Python module plus dependencies. And identifiers are the name of functions, parameters, and variables as shown in this code snippet. We also consider code context, which is the usage of parameters and variables in a function body. In order for the ML model to learn from type hints, we need to create vector representation of type hints. First, we apply common NLP processing techniques like tokenization and stop words removal. Then we train a word-to-vec model to generate vector embeddings. As shown here, each token corresponds to a vector representation using the word-to-vec model. Type4Py neural model is based on two recurrent neural networks with LSTM cells and a linear layer. And as shown here, the input to the model is token embeddings of identifiers, code context, and visible typings. And the output of two RNNs are concatenated with the visible typings and is fed to the linear layer. Finally, the linear layer gives type embeddings to create type clusters. We use triplet loss to train the neural model to learn to discriminate between similar and dissimilar types. The training sample contains 3 data points as shown in the equation: an anchor, positive, and negative. Anchor and positive data points have the same type, whereas the negative data point has a different type. And as shown in this figure, the learning objective is to make positive data point as close as possible to the anchor and far from the negative data point. And finally, to predict type of test samples, we perform k-nearest neighbor search. to suggest types from the learned type clusters. For model training, we use the dropout technique to avoid overfitting, and we used Adam optimizer to minimize triplet loss. And we also employ PyTorch the data parallelism to speed up the training phase. Now I'd like to talk about our type check dataset, which is part of our contribution. First, we perform code duplication using our tool CD4Py. This step is essential to perform to make sure there is no duplication between the training and test set. As a result, we removed around 400K duplicate files from the dataset. And we also augmented our dataset using a static type inference pilot to add more type annotations for variables in the dataset. As shown in the figure, after using pilot, the percentage of type annotation coverage for source files in a dataset is significantly increased. Research has shown that developer provided types rarely type checks, so we performed type checking to have valid guarantee for both training and evaluation. The type checking procedure is explained as follows. First, we apply MyPy to type check the source code files and dataset. 60% of files type check initially, and we ignored source code files with syntax errors, which amounts to 64K source code files. Even the remaining 40K files with type errors, we remove one type annotation at a time from a file. If it type checks, we include the file. Otherwise, we continue to save up to 10 times. And following this type checking procedure, we fix around 16.8K source code files with type errors. After data augmentation and type checking, we ended up with around 201K source code files in the dataset with 1.24 million type annotations in total. And we also split the dataset by source code files. 70% of source code files are reserved for training, 10% for validation, and 20% for testing. This figure shows that the dataset has a tail distribution, and primitive types like string, integer, and list account for the majority of type annotations in the dataset. Before training the Type4Py model, we perform these processing steps. We exclude trivial functions like str and length. The return value of these functions are trivial to predict, and obviously we don't need a deep learning model to predict such functions, to predict a return value of such functions. And we exclude any unknown type annotations from the dataset, and these are not helpful to predict for developers. And we also resolve type aliases to make sure type annotations are consistent across the dataset. Using the type check dataset, now I like to describe the evaluation of Type4Py in comparison with state of the art. Similar to the previous work, type pillows, we consider the exact match and base type match. For example, list string and list string would be an exact match. For base type match, list string and list integer would be a match. As mentioned before, the top one performance is important when predicting types, given that developers tend to use the first suggestion by tool. Therefore, we consider MRR in our evaluation as it considers the rank of predictions. Also, as shown before, our dataset follows a tail distribution. We differentiate between types and we divide them into three sets. The overkitted set contains a string, integer, list. These are primitive types. And also common types are seen more than 100 times in a training set, and we also consider rare types, which is seen less than 100 times in a training set. This way, we can observe how the models perform by ignoring overkitted types, and to basically observe the performance of the models on common types and rare types, not just overkitted types. Overall, we have formulated 3 research questions to evaluate our proposed approach. Considering top 1 and MRR, Type4Py significantly outperforms both typeless and typewriter. Also, Type4Py obtains 100% exact match at top 1 for overkitted types, which is remarkable. In the second research question, we consider 3 prediction tasks, arguments, return values, and variables, and we also consider MRR score and exact match here. And Type4Py considering the argument task, it obtains 64.2%, which is higher than Type and typewriter. Also considering return task and variables, again, Type4Py outperforms both Type and typewriter significantly. In the third research questions, we want to measure the effectiveness of proposed typings and to see how Type4Py performs with different considered typings. We found that code context has the most impact on the performance of Type4Py, and by ignoring visible typings, the MR score drops by 14%, which is significant. Also, identifiers have a positive impact on the performance of the Type4Py model, and also by limiting type vocabulary to 1,000 types, the MR score of rare types drops significantly by 7.2%. At this point, I'd like to talk about the deployment of Type4Py in practice and its VS Code extension. Here, you can see the deployment of Type4Py at the high level. At the client side, we have a VS Code extension. The VS Code extension can either query the Type4Py local model or the production models that is deployed on our Kubernetes cluster. For deployment, we converted the pre-trained PyTorch model to the ONNX model that provides faster inference. Also, we have developed a very small fast application with the predict endpoint, a post request. And as mentioned before, we also provide a VS Code extension on the Visual Marketplace. As of this recording, it has more than 1,000 installations. This is an example of type auto compilation from the VS Code environment. And based on user consents, we gather telemetry data from VS Code environment, and we have a prediction request table as shown here that stores data like activation ID from VS Code, session ID, and processing time. We also have another table for accepted types, which stores accepted type, its rank, type slot, for example, parameter or variable return value, and also whether the prediction window is canceled or not is also stored in the table. I would like to point out that we do respect users' privacy by asking explicitly whether they want to share their usage with us or not. And here are some telemetry stats. In total, we have around 93,000 prediction requests, and from VS Code, we have around 65,000 predictions. And approximately, we have around 127 users from VS Code, and number of accepted types are 119, and number of rejected types are 49. And also, average processing time of prediction request is around 786 milliseconds. And given that our telemetry data for accepted types are small, we cannot really draw a conclusion on the performance of Type4Py in practice. To compute our work using a type check dataset to train and evaluate ML-based prediction model to make sure that we have valid ground truth to evaluate our proposed approach. We also consider the MR metric, and we showed that Type4Py significantly outperforms typeless and typewriter. Type clusters also enables a much larger type vocabulary. And also, I would like to point out that Type4Py cannot synthesize types, meaning that it cannot predict types beyond learned type clusters. Last but not least, our VS Code extension is one step towards to improving developers' productivity. Considering the future work, exploring pointer networks might be a promising direction to suggest new types. And we're also interested to study how to improve Type4Py performance from its usage in VS Code and the available telemetry data. And one more future work can be also about complementing Type4Py with static type inference. To foster future research, we publicly release the code and the dataset on the internet, and also the preprint of the paper is available on archive. And thanks for watching this video, and thank you for your attention. If you have any questions, remarks, or comments, you can reach out to me on Twitter, or also you can also send an email.